This is lesson 3.6 on graphs of polynomials. So when we look at the graph of a polynomial, we can actually, if all we want is a sketch of the graph, we can boil down what we need to look at to really just two different things. We need to look at where does the polynomial cross the x-axis, so in other words, where it's zeros, and then also within that, how do they behave at those points? And also, what happens for very large x? So what happens as our graph goes to the right and to the left? Or in other words, what happens as x goes to positive infinity or x goes to negative infinity? X is getting very, very, very large, both in the positive and negative direction. We can actually determine what those two things are fairly easily once we have our polynomial factored out. When we have it factored, we know that we'll have zeros corresponding to the linear terms of the factorization, and the multiplicity is actually going to tell us what the graph does at each of those zeros. Similarly, the behavior of the graph for very large values of x, that can be determined by looking at the overall power of the polynomial, and that can be determined by just looking at the powers of the individual terms when it's factored out, as well as what the leading coefficient is, what's going to be the biggest number, rather what's the number next to the biggest power of x. So when we're talking about the behavior at the zeros, what we're going to do is, again, to find the zeros, we're going to look at the corresponding linear terms. For the irreducible quadratics, those actually won't correspond to zeros for our graph. Remember, irreducible quadratics correspond to complex zeros. When we're drawing this, we're drawing this on the real plane, so there's nowhere to talk about complex zeros. So the irreducible quadratics actually won't have a direct impact on what the zeros are. They do impact the overall graph, but they won't impact, they won't have an actual zero on the graph. So we will look at the zeros as well as the multiplicity of the zero. If the zero has an even multiplicity, the graph of the polynomial is just going to, basically it bounces off of the x-axis. So if you think about what the graph of y equals x squared looks like, the graph y equals x squared goes down to x equals 0 and just kind of bounces off the x-axis right at x equals 0. However, if it is an odd multiplicity, it's going to cross right through the x-axis at that point. So an example you can think of is y equals x cubed. At 0, the graph of y equals x cubed crosses right through the x-axis. Now for large values of x, as x gets very big, our y values are going to get very big. So as x goes to positive or negative infinity, y is going to go to negative infinity or positive infinity. Which one it goes to, though, is going to depend on what polynomial we're working with. As I mentioned before, we need to look at two things. We need to look at the power of the polynomial, that's the biggest power of x, and its leading coefficient. The leading coefficient, all we need to do is to see if it's positive or negative. We don't need to know the actual number, just if it's positive or negative. Once we know those two things, the behavior of the graph for large values of x, so again, as we go very far to the left on our graph, or as we go very far to the right on our graph, it's going to break down into one of 4 different categories. So rather than trying to explicitly state those 4 categories, let me direct your attention to the graphs of these 4 very basic functions that we've encountered before. The graph of y equals x squared, the graph of y equals negative x squared, the graph of y equals x cubed, and the graph of y equals negative x cubed. If you look at each of these, so for example, let's look at y equals negative x squared. If you think about the graph of y equals negative x squared, as we go to the left, my y value is going to go to negative infinity. As I go to the right, my y, my y value also goes to negative infinity. So what we're going to do is, if we're in a situation where our polynomial has a negative leading coefficient and an even power of x, its behavior for very large values of x is going to be just like that of y equals negative x squared. As we go far to the left, my y value will go down, so it'll go to negative infinity. As I go far to the right, my y value will go down. It will go to negative infinity. So we can break this down into 4 cases depending on whether or not the leading coefficient is positive or negative, and if the power is even or odd. If you can remember what the graphs of these 4 simple graphs look like, you can determine what's going to be the behavior for large values of x for any polynomial. Okay, so let's take a look at this one. So sketch the graph of y equals 2x cubed times x plus 3 squared times x minus 2 to the 4th. So this tells us that we have zeros at 0, negative 3, and 2. So what I'm going to do is I'm going to go ahead, draw my x and y axes. I'm going to go ahead and put points on here just to denote to myself, all right, I have a 0 at 0. That's from my 2x cubed term. X plus 3, that tells me that I have a 0 at negative 3. So let's see here. So negative 1, negative 2, negative 3. So I have a 0 at this point as well. And then x minus 2 tells me I have a 0 at positive 2. So I have 3 zeros here. So x equals 0, x equals negative 3, and x equals 2. I'm going to go ahead and make note too of the multiplicity for each of them. The multiplicity for 0 is 3. So I know that that means that I'm going to cross through the x-axis at 0. Now I don't know from which direction, if I'm going to go this way or this way. I don't know that quite yet, but I'm going to keep track of that because I'll know later on. X plus 3 squared, multiplicity is 2, so that means I'm going to bounce off of it. X equals 2, multiplicity is 4, so once again that means I'm going to bounce off of the x-axis at x equals negative 3 and 2. Okay. The next thing I need to do, I need to look at the biggest power of x. So the biggest power of x, I could multiply all this out, but there's no need to. That's going to be a big old mess. Since we have linear terms here, it's very easy for us. Just add the exponents. So 4 plus 2 plus 3, that's going to be, let's see here, 6 plus 3, so 9. So the power is 9. What really matters here isn't that it's 9, it's that it's odd. Furthermore, I'm going to look at the coefficient. Notice that here, my linear terms, I'm generally going to help you out and leave these as being just 1. So really all you need to look at is this number right here. So my leading coefficient is going to be 2. And again, what matters isn't the number, it's whether or not it's positive or negative. So the coefficient is positive, my power is odd. So what I want to do is I want to keep in mind, what does the graph of y equals x cubed look like? X cubed because it's an odd power of x, and positive x cubed because the coefficient of my polynomial here, the leading coefficient of the polynomial, is positive. So I know that the graph of y equals x cubed looks something like this. So what's important is as I go to the right, my y value gets bigger. It goes up. It goes to positive infinity. As I go to the left, my y value gets more and more negative. It goes down. It goes to negative infinity. So on my graph here, I know that as the graph goes to the right, that my y value is going to get bigger. It's going to go off to infinity. So from this point right here, I know that my y value gets bigger. So I'm going to go ahead and just draw it like that. Now, this is just a sketch, an honest-to-goodness sketch, so don't worry about the exact shape of what this needs to be. Once you know what happens here, you basically are done. You just have to fill in the rest of the information. All right, so at x equals 2, my multiplicity is even, so I know that I'm going to bounce off of the graph, off of the x-axis, so my graph is going to do something like this. At x equals 0, my multiplicity is odd, so I'm going to cross through the point there. And I return here. At x equals negative 3, my multiplicity is even, so once again, I'm going to bounce off of the point there. So my overall graph is going to look something more or less like this. This is as far as I want you to go for these. Give me just a general shape. What happens as x gets very big, as we go to the left, as we go to the right, and what happens at these 0 points. Notice at negative 3 and at 2, my multiplicities were even, so see how the graph bounces off of those points? Whereas at 0, my multiplicity was odd, so I crossed through it. So if you keep these two things in mind, what are the zeros and their behavior there, and what happens as x gets very big, as it gets very negative and very positive. If you can figure out those two things, you are in great shape. So this is just our final answer right here. So for the drill quiz, this is what I want you to do. It doesn't have to be perfect. If you compare this with what a graphing calculator might tell you, it might look a little bit different as far as how far down this goes or how far up this goes. Don't worry about it. Again, show me what happens as x gets very big, very positive or very negative, and show me what happens at these 0 points. As long as it's clear and correct what's going on there, you're going to be perfectly fine. So here's another one. So sketch the graph of -3 times x plus 2 cubed times x minus 1 times x squared plus 2x plus 5 squared. So let's go ahead and keep track of our zeros. X plus 2 I know is going to give me the 0. X equals -2, and it has multiplicity 3. X minus 1, that's going to give me the 0. X equals 1. And notice, I don't have an exponent specified here, so remember there's always an implied exponent of 1. And then this last term, it's an irreducible quadratic. So remember from our last section, this is going to give us imaginary zeros. We do not plot imaginary zeros when we sketch the graph. So this is going to affect the overall power of the graph, but we aren't going to have an actual 0 from this. So we only have 2 zeros on this graph that we're going to draw, -2 and 1. The overall power is going to be a little bit trickier though because of this quadratic. This x squared plus 2x plus 5 squared term, this isn't going to be, we're not going to add this up as power 2, it's power 2 times 2, so power 4. So the overall power of this polynomial is 4 plus 1 plus 3. So altogether that's 8. Again, what matters here is that it's even. The next thing we need to look at is the leading coefficient. Again, I'll work it out so that really all you need to look at is what this number right here is. The leading coefficient is -3. What matters is that it's negative. So we want to think of our simple graph that has even power and a negative coefficient. So we want to look at the graph of y equals -x squared. That's going to help us figure out what this graph does as we go to the left and the right. So y equals -x squared looks something kind of like that. Okay, so I'm going to sketch the graph for this polynomial. I'm going to plot my 0, so I have a 0 at x equals -2. So here's -1, -2. So I'll put a point there. And at +1. So I'll put a point there. All right, at +1, I know that I'm going to cross through the x-axis because it has odd multiplicity. And at -2, I'm going to cross through it because, again, it has odd multiplicity. Okay, looking at my rightmost 0, I know that since this is going to behave just like my y equals -x squared graph, my graph is going to go down kind of like that. Maybe not the exact same shape, but that's okay. We're just sketching this. We're just getting a general idea. All right, at 1, I have an odd multiplicity, so I know I'm going to cross through at this point. Go on to my next 0. At -2, I have odd multiplicity, so again, I'm going to cross through. So my graph looks something kind of like this. That's all we need to do. We've shown what happens as x gets very big, and we've shown what happens at our zeros. So for the matters of just sketching this graph, we've done exactly what we need to do.